It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Oh, hi. Sorry. Didn't see you there. Well, I guess we'll listen to Tom Petty and start talking about free fall motion. Good evening, everyone. Welcome to Tibbetts Physics. What is crappin' in? Today, we are going to go through a problem on our free fall motion jigsaw. Let's go to the second page. We have a chart that we created in class for vertical motion only. We'll add horizontal motion in the future, but for now we're going to focus on just the vertical aspects. So let's look at what we know for vertical motion when an object is going straight up in the air from the bottom to the top. We may know the initial velocity. It can be given to us, but not necessarily. We know that the final velocity at the top is 0 meters per second, and the acceleration due to gravity while the object is going up in the air is negative 9.81 meters per second squared. When an object is going downwards, so from the top down, or if it's just dropped, this time, because it starts at the top, the initial velocity is 0 meters per second. The final velocity is negative whatever vi is from going up, so negative initial velocity from going up. The acceleration is speeding up as it's moving downwards, so it's negative still, 9.81 meters per second squared. If we know the distance to go up, we can just call it d. So I'll use a different color. The distance to go up is d, some number maybe. It's the same number to go down if you catch it or if it lands at the same position that it started from. If we want to calculate the total distance it traveled, we just double the number to go up or the number to go down. If we get the time to go up, we just call that t for now, so some number. If it lands at the same spot it started from, that's the same as the time to go. The time to go down is the same as the time to go up. And if we want to get the total time to go up and down, we can just double that number. To do our calculations, they're the exact same calculations from the constant acceleration units. So we have 3 acceleration formulas that we could look at. One is v sub f equals v sub I plus a times t. The other one is vf squared equals vi squared plus 2ad. And the last that we could use is d equals vit plus 1/2 at squared. With these formulas, we can determine either, you don't have to write this down, but we can determine either the initial velocity an object was launched off at, how high it went, the time it took to go from the bottom to the top, or we can calculate the distance to go down, the time to go down. We know the final velocity at the bottom is equal to the initial velocity when it's going up. If we want to find the total distance, we double it. The total time, we double it. Let's do one problem together. Number 1. An object is dropped from a building on Earth at a known height. In this problem, we can assume we know how high the object falls. It's only going downwards because we dropped it. So in this case, we don't care about the up, and we don't care about the total. So we're just going to focus on the going down part. We know that on the height it falls, so that's D. We'll put a check mark. We know the acceleration due to gravity on Earth. I'll just put a check mark. It's negative 9.1 meters per second squared. Because we drop an object, the initial velocity at the top of its path is 0 meters per second. And what we want to do is find the time of flight for this question. Looking at our formulas, we know VI, AD, and we're finding T. As all three of those variables is D equals VIT plus 1/2 AT squared. D equals VIT plus 1/2 AT squared. VI is 0 meters per second, which means VI times T is 0. So that leaves us with D equals 1/2 AT squared. We want to move every variable away from T. If we look at the 1/2 to get to the other side of the equal sign, we'll multiply both sides by 2. That leaves us with T. To move the A to the other side, that's attached to T squared, because it's multiplied by T squared, we have to divide both sides by A. And since the time is squared, to get rid of that square, we have to square root both sides. That leaves us with the time is the square root of 2D over A. So that'll give us how long it takes the object to fall. Let's do some proportional reasoning. If the height of the building is quadrupled, by what factor would its time of flight change? T prime is proportional to, we keep the square root. 2 is a constant, so it can turn into a 1. The height is quadrupled, that's D, let's turn it into a 4. Acceleration in this case is a constant, so we'll turn it into a 1. And the square root of 4 over 1 is 2, so the new time is 2 times the old time. So if you quadruple the height of a building, it's going to take twice as long to fall. Letter B. If the height of the building is 1/25 as high, by what factor would the time of flight change? Let's call this T double prime. It's proportional to the square root. 2 is a constant, so we keep it, we'll turn it into a 1. D, the height of the building now becomes 1/25. And that's all over 1 for the acceleration, which stays constant, times the original time. The square root of 1 over 25 becomes 1/5 of the time. So if we cut the building by 1/25, the time of flight will be cut by 1/5. That's it for this video. Thank you for watching, and I'll see you next time. See ya.